This is a tutorial on how to run a one sample t-test in an SPSS. So this is using data from the textbook chapter. And so one thing I want to start out by saying is that I'm just going to use the same data that is from the textbook chapter and the example that they use. When you do your lab assignment, there's going to be a different set of data. So don't just start working on this along with me, thinking that that's going to be your lab assignment. So you have different data. So what I want you to do is the idea here is that this is going to just show you how to do one sample t-test, work on some of the interpretation alongside it. I'll show a couple places where you might make a mistake, but then the hope is that you're able to kind of take that knowledge or take that new skill and be able to generalize it on a new set of data. Okay, so this is just to show you what you need to do, but this is not the data that you're going to be working with. Okay, so the data that the textbook authors use, it's again one of these kind of silly examples where we've got 30 participants and they're given a measure which is called the Zombie Opinions Measure Form B, or Zombie for short. Isn't that clever? So we've got 30 people that were given this opinion measure, and we can interpret higher scores as meaning a more favorable attitude towards zombies. You also see that there's a Zombie-2. This is the same measure given to the same 30 people, except after they went to zombie rights sensitivity training workshop. Okay, but we can interpret the scores in the same way. Higher scores mean more favorable attitude towards zombies. And then we're going to see this variable in the middle is a group variable where participants were either categorized as having been chased by zombies before or never chased. So if you just toggle back and forth, what you'll see is that what we have to do in SPSS is we have to provide this numerical value. And so the way that we did that is we can go back to our variable view. You'll see that we've got our two zombie opinion measures, zombie and zombie2. These are of course scale, but to create our nominal variable, we had to enter value labels that are associated with each value of the variable. So we had to go in and enter 1 is equal to chased and 2 is equal to never chased. And so you need to, when we do, so this chapter you actually learn 3 t-tests, and I'm going to only show you the first of these t-tests today, the one sample t-test, but I've set up the data this way, and so when we do an independent samples t-test, we do that with a group variable, and so we need to set up the data this way. Okay, so I'm just showing you the data now, and we'll come back to this data. Actually, with in the next 2 tutorials, I'm going to show you the paired samples t-test and the independent samples t-test. But for today, we're just going to do a one sample t-test. We use a one sample t-test when we have a single sample of participants, and we're interested in comparing the average or the mean in that sample to a known population mean, but when we don't know the standard deviation of the population. So in order to do a one sample t-test, you have to know the mean in the population, or you need to be able to have a reasonable assumption about what it is, or you need to have some logical comparison value to compare your sample mean against. So in this case, we have to know the population mean, and in the example, the textbook authors gave that to us. So what I'm going to show you in this tutorial is we're going to run a one sample t-test for this variable, and we're also going to run a one sample t-test for this variable. Essentially, we're answering the research question, does the mean in this sample differ in a significant way from a known population mean, which in this case was 10? And then we're also going to basically answer that same question, except this time we're just going to ask, after they attended this zombie rights sensitivity training, does the average opinion in the sample differ from the known population mean? All right, so here's how we perform a one sample t-test. Actually, for all of our t-tests, we're just going to use our Analyze menu. And when we drop down here, we'll see that there's an option to compare means. So we've got our one sample t-test, independent samples t-test, paired samples t-test, as well as another statistical procedure that we're going to learn, which is a one-way ANOVA. So they're all here in their compare means menu. So we're going to select the one sample t-test. And then here we've got the option to include all the variables that we want to run a one sample t-test on. So I'll just go ahead and include our first variable, which is just the zombie opinions measure. I'll do the other one next. And I'm only doing one at a time because I want to establish the practice. You don't necessarily always have the same test value for each variable. Okay, so the test value is our known population mean. This is where we enter what is the value that we want to test our sample mean against. So what is our known population mean? Or you might have heard the term mu, which is the Greek letter mu, which is the symbol for population mean. Okay, so this, again, this value was given to us. We have to know this. We have to have either a logical comparison value or a known population mean. In truth, that's pretty much all there is to it. You'll see that there's an option button here. All this does is give us the option on how to handle missing values. We don't have any missing values in this example. And then we also have the option to specify a confidence interval percentage. By default, we always use 95%. And so that's why that's specified in SPSS. So we don't actually have to do anything there. You'll see the bootstrap button. That's for a more advanced procedure that we're not going to learn in the class, so don't worry about that. I actually don't know in your version if you have this option to estimate effect sizes. I do, so I'll show it to you because I think it's worth knowing, but it's actually something that you can hand calculate very easy, even if you don't have this option. So perhaps let me know if you've got that option. I certainly have it in my version, which I think is the same as yours, but let me know. So that's it. All we have to do is we're going to do a one sample t-test on our zombie measure against a test value of 10. I'm going to paste it. And then we are going to open up my syntax. There we go. Highlight, play it. You could just hit the OK button. You don't have to paste it. All right, so here's our output. Let me just go through the tables. First table is our table of descriptive statistics. So we've got N is 30. We knew that we had 30 participants. Here's their sample mean. Okay, so their average opinion on the zombie measure was 10.2667 with a standard deviation of 6.09 about, and then a standard error of the mean. Realize that standard error of the mean might not be a familiar concept to some of you. It kind of depends if you've already taken stats class or where you're at in stats class. Maybe you're going to get to this concept, you just haven't gotten there yet. I actually recorded another tutorial, which is a conceptual overview of the one sample t-test, as well as null hypothesis significance testing in general. So I'd highly encourage you to check that out if you just want more background on what do all these numbers actually mean anyway. But I can go through a very quick interpretation of what the standard error of the mean represents, which is just the average amount of error that we expect when we sample just any given mean. We just randomly sample a mean from a population based on samples of size 30 with a population standard deviation that we can estimate. Okay, I actually went in a little bit more depth there than is necessary. You can just interpret this number as saying, anytime we take a sample, we expect that our mean is going to be in error. Our sample mean will be in error to some extent as an estimate of our population mean. This number tells us the amount of error we can expect to have when we use our sample mean as an estimate of the population mean. Okay. Another interpretation would be anytime we randomly sample from a population, when we have 30 participants and when we can estimate what the population standard deviation is, this is about how much we can expect our sample mean to differ from the population mean just randomly because of that sampling process, because we've got 30 participants and not every single person in the population. So ahead of time, it's a kind of a valuable number to know because we're saying to ourselves, all right, our test value is 10. Okay, 10 is the known population mean. We got a sample mean of 10.2667. We expected kind of the average amount of difference like a typical amount of difference that we were likely to get via that random sampling process would be about 1.11. So right now that tells us that the difference between our sample mean and the population mean, which is captured right here as with the mean difference, that's not a big amount. Like our sample really doesn't differ that much from our population mean. That's what the standard error tells us. Okay. Now, what we actually do, this is a one sample t-test, what we actually do is we calculate a t-test and we come up with a t-statistic, which you'll see right here. So our t-statistic is 0.24. We get that t-statistic by dividing the mean difference that we actually observed between 10.266 and 10. Okay, so the difference is 0.2667. We divide that mean difference by the standard error. Okay, so basically the t-statistic is a ratio of the actual difference that we saw between our sample mean and the population mean, kind of over or divided by the kind of amount of difference that we would expect just via a random sampling process. Okay, so that's what our t tells us. And then really to get to the punchline, what we want to know is, well, is that a statistically significant amount? Like, is this mean difference, like we are observing a difference between 10 and 10.2667, but is that mean difference of 2.667, is that a statistically significant difference? And that's what this column tells us. So statistical significance by definition means that our sample result, or in this case our sample mean, is a large enough value to only happen via a random sampling process from a known population. Okay, you would only get a sample mean that would happen via that random sampling process less than 5% of the time. Okay, so that magic less than 5% of the time. Okay, so statistical significance is a result that happens less than 5% of the time if the null hypothesis is true, or we could say we'd get a sample mean this large from a known population mean less than 5% of the time. So the number that we're looking for here is something less than 5%. In other words, it's a number that is less than 0.05. Okay, statistical significance equals less than 0.05 in this column. What we can see here is that this significance is 0.812. So that's basically a probability of 81.2%. Okay, so we're basically saying that the likelihood of getting a mean that big or bigger when sampled from a population with a mean of 10 is 81.2%. So like it's likely, it's probable. Okay, and statistical significance is about sample results that are unlikely or improbable, specifically happening less than 5% of the time. So we're going to look here, and if this number is less than 0.05, statistically significant. If it's not statistically significant. And this is a departure because if you've been learning null hypothesis significance testing in your statistics class, the procedure that you've learned up to this point most likely is to compare your t statistic to some critical value of t. Okay, your critical value of t being some cutoff or some threshold that you need to exceed. And it's this kind of binary decision. If my t statistic exceeds the critical value, then I have a statistically significant result. That's the same process that's actually happening here. Okay, so what we would have in this case is that this t, you can see how small it is, this would not have exceeded a critical value. But what SPSS does is it kind of goes one step further and it says, I don't need to show you the critical value, I can just tell you the exact probability of obtaining a t that is this large or larger. And because of our definition of statistical significance, things that happen less than 5% of the time, I'll just tell you the probability and you can make your decision that way. Okay, so it's slightly different than what you learned about in stats class, but we just have the exact probability associated with our sample result. All right, the next thing that we'll see in this table is a 95% confidence interval around this difference. And so what we're basically saying is we come up with a confidence judgment that is going to allow us to be 95% confident that the true mean difference, kind of the range of values that contains the true mean difference between our sample and population. So what this is telling us is that we could be 95% confident that our this sample of people actually come from a population that would have an opinion that is 2 points less than 10. However, they could also come from a population that has an opinion that is actually 2.5 points more than 10. So you can see like not a lot of confidence around our judgment. It's like this particular sampling process could result, like if we kept repeating this process, we could get there's a wide range of values that we could get for this mean difference. So that's what it's telling us. It's giving us a 95% interval at which we expect the true mean difference to fall, given the sampling error that we have in our data. Okay, now this is the effect size estimates. I go over in the tutorial that I give you is the conceptual tutorial, basically what Cohen's D is as a statistic and kind of what it means and how to interpret it. What you're looking for your actual value of Cohen's D is this point estimate column. And we won't even worry about this bottom row in the table. SPSS often gives you more output than you need, and in some cases when you're taking the introductory statistics class, more than you're ready for or more than you're familiar with. But Cohen's D is a statistic that many of you, if you're not familiar with it now, you will be soon enough. Cohen's D is simply the difference between your sample mean and population mean divided by the standard deviation. Okay, so slightly different interpretation than the T statistic, which is your mean difference divided by standard error. Here, Cohen's D is your mean difference divided by standard deviation. Okay, and so this is a standardized metric, and it tells us basically how to evaluate the difference between means, or kind of the effectiveness of like a treatment effect that would make one group different from another. And so I post some guidelines in the conceptual tutorial, but that's one bit of output that you can get, so that in addition to making a judgment about statistical significance, we can also say something about the size of the effect. As you might expect, beg your pardon, a point estimate for Cohen's D of 0.04 when you look at guidelines is not a big effect. It's a very small effect. So what we're saying is there's really not, in addition to not being a statistically significant difference, there's only a small difference between the sample mean and the population mean. All right, let me just go ahead and run the other result. And I did this, I'll move this out, and I did this just to show that, not all your variables will necessarily have the same test value. This one does, so go ahead and run that. Okay, here we can see that in this case now the mean after sensitivity training is 12.8. Standard deviation, standard error. What we do is we go straight to our T statistic. We see that it's larger, and in this case now our statistical significance is 0.024. It meets that threshold of being less than 0.05. So in this case we do have a statistically significant difference between our sample mean and the population mean of 10. Okay, so our mean difference of 2.8 is statistically significantly different. One thing that you'll notice is that in the 95% confidence interval of this difference, you see that there's only positive values here. So what this is saying is that we can be 95% confident that the true difference between this group of people and this kind of known population value, we can be 95% confident that there is some positive difference. Okay, that after sensitivity training, they have a higher mean. You'll notice here that we have this confidence interval straddles 0. Okay, so what we're saying is that we can't be, in order to be confident that 0 difference is in this interval. Okay, so when we don't have a statistically significant result, we're going to get our mean difference. The confidence interval will contain 0. When we do have a statistically significant result, the confidence interval will not contain 0. So if we have a positive mean difference, you're going to get positive values for your confidence interval. When you have a negative mean difference, you're going to get 2 negative values for your upper and lower confidence interval. Okay, here we can go to Cohen's d. We see that we have a point estimate now. We went from 0.04, we now have a point estimate of 0.43. We just have a larger effect, don't we? We have a larger mean difference, a larger effect, and so that is now statistically significantly different. Let me show you one place where you can mess up, which when we're comparing means and we do our one sample t-test, let me reset everything. I'll put in our first value. If we don't change the test value, this is what we can get. Okay, so in this case, here's our first mean of 10.266. Our test value was 0 because we didn't change the default. So what we're telling SPSS is that the mean difference is 10.266. That is, where we have a sample mean of 10.266, and we want to know if that is statistically significantly different from a population with a mean of 0. Well, yeah, there sure is. Look at how big this t is, and then you'll see a significance value of 0.000. That does not mean that the probability is 0. It just means that the probability of sampling a mean of 10 from a population of 0 is something very, 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 very small, highly, highly improbable. It's like 0.00002 or something like that. So the short of it is the number just got truncated. It got rounded off because it's something smaller than like 0.001. Okay, so I get this sometimes from students who are like, well, the probability is 0. No, impossible. There's no such thing as a 0 probability. There's always some probability associated with some random event. It just means that that probability, in this case, is so small that SPSS had to like chop off the digits. So that's all we're seeing there. But this is, and then you can of course see how big that effect is. But this is just because we specified the wrong test value. We specified the wrong value for the population mean. So make sure when you're going in there and you're running that one sample t-test to make sure to put that test value in there. Okay, I think that's it. That's really all there is to it. It's fairly straightforward, running a one sample t-test. So good luck with your lab assignment this week. Hope you found this tutorial helpful.